So it's my great pleasure to introduce our speaker today, Dr. David Hadka, who is actually one of my former advisees. So he took my grad class at Penn State on evolutionary computation in, I guess, 2008. And then he was one of these interesting students that sort of sat in the room, pretty calm, much calmer than a lot of the other students. And it was always clear exactly if he was like resonating with the material or not, until I got his project for the semester, which instead of exploring an algorithm, he created a framework for actually simulating and evaluating nearly all of the algorithms that we were discussing, which eventually led to MOEA framework and a software framework that has served thousands, if not tens of thousands of individuals. True to his nature, that sort of calm, collective, but disruptive-minded individual wasn't satisfied with sort of thousands. So he's going to be presenting to us today what it's like when you're servicing millions. And so with that, Dave, I'll hand it off to you, and looking forward to your tour of cloud computing. Thank you.
Yeah, thank you, Pat. Pleasure to be here today, and thanks everyone for joining, or if you're joining asynchronously, thank you. So yeah, my talk is about building scalable software, and specifically how we do that with cloud computing. So there we go. So quick background of me, as Pat said, I was a former student of his and got a BS and PhD in computer science and engineering. And for about 5 years after I graduated, I worked at Penn State Applied Research Lab as a research engineer. And then in 2017, I basically left academics, switched completely to industry, complete shift in what I was focusing on, and joined Microsoft, where I worked for the Cloud and Enterprise Group. And then essentially just last year, joined GitHub, which was bought out by Microsoft. And so that's where I am today. And a lot of what I'm going to talk about is based on my experiences at Microsoft and GitHub. So quick idea of what I do at GitHub, to give you an idea of kind of the scale that we operate at. I work on a product called Github Actions, and it's actually a new product that GitHub launched in late 2019. And basically, it's an automation system for your code. And we call it, in the technical term, a CI/CD system, continuous integration, continuous delivery. And it's basically a system where you can automate how you build, test, and deploy your code. And all of it's done by GitHub. So GitHub provides all of the computing power to run your automation. And what this looks like if you're going to use it, here I show a repository that I just created. And you will see that there's this Actions tab at the top. And when you click on that, it will give you some information, but also gives you this option to set up a workflow. And a workflow is basically the set of instructions that you're going to run. It's your automation. But what we've actually done for you is we've gone and looked at all the different programming languages and tools you might want to use, and we've created these starter workflows. So if you're using Python or R or MATLAB, you can just go in and find your language of choice, click set up this workflow, and it's going to give you a basic starter workflow. And in this case, this is what it will look like for Python. I'm not going to go into too much detail here because there's a lot, but the idea is that Actions lets you set up these workflows, and we can have triggers based on different operations that you might perform on GitHub. The most common one would be pushing code changes or creating a pull request. So this says, if we're going to make any code changes, we're going to run this workflow. And down here under steps, we will check out your code. We're going to install Python on this machine that's running someplace in the cloud. We're going to install all of your Python dependencies, and then finally run your Python tests. And so what that does as a software developer or someone who's developing code on GitHub is every change I make to my code, I'm going to be running the suite of tests that I've written. And as it runs, it's going to eventually say, my tests have passed. It'll give you that green checkbox, or you might give you red X if some of your tests failed. And then we can go back and fix the code. So that's a quick overview of what GitHub Actions is. as I mentioned at the beginning, we launched this product in November 2019. And as of today, we are consuming over 50 years worth of computing time every single day. And what's really exciting about that is most of this computing time that we use is essentially given completely free to the open source community. So there are hundreds of thousands of open source projects on GitHub today that are using GitHub Actions to automate all of the workflows, to test their code, and to deploy their code. So it's been really exciting to be a part of this entire process. So the talk today, going to talk about kind of how we're able to build a system like that that can scale to 50 years of computing power, all calculated in one day, which is astonishing. And all of that's done by leveraging the cloud. And so going to talk about like the tools and techniques that we use to make that all possible. Start off, wanted to talk about what is the cloud. So I'm sure most have probably heard of cloud computing as kind of the big modern thing. But very generally, it's the delivery of computing services over the internet. So that means all of your compute, so like your virtual machines, all of your storage, your databases, networking, all of that is provided for you over the internet by these big public cloud providers like Microsoft, Amazon, and Google. And one of the big advantages of this is that these big companies can use economies of scale to make these cloud services very cost effective. If you imagine 10 years ago, if you're a startup company and you want to build a service that can be used by millions, you'd have to invest a ton of money, buy your own hardware, hire engineers to go and build that system and maintain it. And it requires a huge capital investment. But by essentially letting these huge cloud companies do that for you, it's much cheaper, and you also only pay for what you use. So whether you're an individual or a huge company, you're paying for only what you need to use, and you can also scale as your product grows over time. And what's really cool about all of these different public cloud companies is they make it extremely easy to use. So I'm going to focus mostly on Microsoft Azure, which is Microsoft's public cloud, but the same goes for Amazon and Google and other cloud providers. So say I want to go and make a new resource. I'd log into the Azure portal and click the button, create a resource. And I get to this page where it lists all the different resources I can provision. And there's hundreds of these. You have Windows servers, you have Ubuntu server, you have SQL database, storage accounts. In this case, I might want to create an Ubuntu VM. So when I click that, I go to a new page where I just fill out a few details of what I want. I give it a name, tell what region I want to run in, select the size of the virtual machine. So I can say I want to run on a 4-core 16-gigabyte machine. And then I click create. And in about 5 minutes, I have a working Ubuntu virtual machine provisioned someplace in the cloud that I have access to then. And so you can see it's extremely easy to get up and running with this. And in fact, this has been a wildly successful business model. This year alone in 2021, the public cloud revenue is forecast to exceed 300 billion. So it's been wildly successful and profitable for companies like Microsoft and Amazon. And just to give you an idea of the scale that we're talking about, this figure here shows the Microsoft Azure cloud. And each one of these blue circles you see on the screen is a data center region. And within each region are multiple data centers. And each of these thin blue lines is a dedicated high-speed network that is set up by Microsoft. It's a private network that Microsoft owns or leases that is strictly used for cloud traffic. So with that, we're able to provide services anywhere in the world with very high speed. And as I mentioned, each one of those points is a region that has multiple data centers. Give you an idea of what a data center is. This is an example of a recently built data center in Cheyenne, Wyoming, that is 200 megawatts. So that's using about the power at 32,000 homes. So a medium-sized town, all located in this data center. And you can see it's a massive facility. It's connected to the local power supply. It has its own air conditioning, power backup, et cetera, for all of the operations it might need. And the other cool fact about this is Microsoft is operating 160 of these data centers. So you can imagine that this is just an absolutely massive investment in the public cloud. So as a developer, how do we actually go about building a global service using these cloud resources? So if I were to design a new service from scratch, I will be using some basic building blocks, and these building blocks are provided by the cloud. As I mentioned, I already showed we can create virtual machines and control those sites. We might need something like a file storage. We need a database, maybe. You need a network to connect all of them so you can communicate. And that's kind of the basics that you might think of a service, but there's also a bunch of additional services you might need. Security is a big one. How do you protect all of this data from attackers? Do you need a firewall? Do you need denial of service protection? If the service is running off in the cloud in some part of the world, how do you monitor the health of the system? How do you collect logs and telemetry? How do you back up customer data and keep that data secure? All that is essentially provided by the cloud, by these companies, but we do need to go and set it up when we're creating this service. So what we end up doing is, at least in Microsoft, we package all of these services, all of these building blocks that we're using into what we call a scale unit. And a scale unit is essentially a independent installation of this service. And as the name kind of implies, it's scalable. And so we're going to use this to scale up and meet customer demand. So how would we actually scale? Well, there's actually two ways that we can do that. One is called vertical scaling and one is called horizontal scaling. Vertical scaling is where we basically take the existing resources we have and we just increase their size, we make them bigger. So we're not adding more resources, we're just increasing the size of them. So in terms of virtual machines, we might go from a 4-core to a 32-core machine, being able to handle much more traffic. But ultimately, there's a limit to how big we can scale that way because hardware has physical limitations. And so the other alternative is horizontal scaling, where we actually add multiple virtual machines or multiple instances of that resource in parallel and usually put them behind some kind of load balancer. And what it turns out is that we actually have to use both of these. But if we're talking about, say, scaling to meet demand from the growth of the service, horizontal scaling is much easier to use because it's much easier to add or remove a virtual machine than it is to increase the size of an existing one. And what I show here is the actual load on a service that we run in production over a 3-week period. And you can actually see that there's a substantial deviation between, you can see the peaks during the day and the drop off at night, and you can also see the weekends. And so we're actually able to automate this entire process of scaling up and down to meet this demand from our services. So that makes this very cost effective to us. So what I talked about there is how we can scale up and down in individual scale units, but even with all of that, there's still limits on how big we can go. And so if we want to go bigger and operate at a global scale, we actually need to split these scale units up into multiple independent units. And so we actually spin up these scale units, multiple instances of them, in key regions across the world. And what's great about that is because we can get close to customers. If we have customers in Europe, we can have a European scale unit. If we're in the US, we can have a US scale unit. And that makes our service much faster because we're closer to customers. In fact, this is what our service looks like. We have 20-some scale units running in production, spread all across North America, South America, Europe, Asia, and Australia. So you can see that using the cloud, we're able to reach a very broad audience with our service. So that's how we can actually scale up to meet demand, but how would we build a service that is reliable? Because ultimately, if we're providing this public service, we want to make sure it works when customers need it. So the first thing I want to talk about is availability and how we measure availability. Because if we're talking about reliability, we need to kind of know what we're talking about there. So we use this term called the nines. And basically what that means is it's a number of nines in the availability percent. So if I say 1 9, I'm talking about 90% available. 2 nines is 99% available. 3 nines is 99.9. Typically, our goal is 5 nines, which is shown here. You can actually go a lot further down, but it tends to become impractical to reach that level of availability when you look at how that actually breaks down into downtime. So 99% availability sounds good, but in reality, that means our service might be down for over 3 days in practice, 15 minutes a day. So that's not that great. When we talk about 5 nines, we're allowed only 5 minutes of downtime per year. So that's actually incredible. And that's the goal that we get there. And we're not quite there yet, but it's definitely something we want to get there. To do that, we can leverage different techniques. What I'm going to talk about here is some of the larger techniques we might use. There's a lot of detail that I'm not going to be able to cover in this talk. One of the key things we leverage is called availability zones. And the idea here is that within a Azure region or a Amazon cloud region, there are multiple physical data centers. Each data center is independent. It has its own power supply, its own cooling, its own networking. And if we can spread our service across each of these data centers, replicating data across them, having multiple VMs. So in the event that we lose a data center, our data still exists. We still have VMs running to process traffic. And so we can lose an entire data center and our service still remains completely functional. You might ask me, hey, Dave, like these are billion-dollar data centers, you just don't lose them. But in reality, you do. And I was actually at Microsoft at the time that this happened, and we lost a data center, the entire data center in San Antonio, Texas, due to a voltage spike, which is basically a lightning strike, that brought down the data center cooling, which then triggered an automated shutdown because the temperature started to increase, which can damage the equipment. So while this might sound excessive to be worried about how do we avoid a data center outage, it actually happens in practice, and it can be very impactful. We during this incident, we found out that we had services that were being impacted because they were only operating out of this data center. So when we lost that data center, some key functionality was just gone. And it took over a day for this data center to come back online. But having said that, what is the most frequent source of outages when we're talking about software? And it turns out that it's actually code changes. So it's actually the developers who are probably the most likely cause, which is pretty funny to think about. But what I show here on the bottom left is project stats for the actual code base that I work on. And we can see that we have over 6,000 commits, 6,000 code changes every single week by 300 some authors. And so you can see that, this code base is constantly changing. There's a ton of individuals involved in this process. It's very easy for one of those code changes to have a bug in it, and that can bring down a service. And this is talking about a relatively small code base. When you're looking at something at the scale of Windows, you have tens of thousands of changes per day happening. You have thousands of authors. So the problem there becomes even more massive. So what can we do about this? So one of the very common techniques used in the industry today is what we call CI/CD. And I mentioned it at the beginning when talking about Github Actions. But it basically stands for continuous integration, continuous delivery. And all that really means is that we want to make incremental code changes frequently and reliably. And I depict that in this diagram on the right here, showing there's this very tight loop between coding, building, testing, releasing, deploying, operating, monitoring, and planning. And all this really means is that there's this very tight feedback loop between the code we're writing, the tests we're running against it, we release into production, we make sure that the code isn't causing any issues, and then we get feedback from that and make changes to the code as necessary. But by splitting up these changes into very small incremental code changes, we're able to reduce the risk of deploying code. So to get to that point, we really need to make sure our testing is good. So we want to be able to test earlier in the cycle and test more frequently. So if you've had any background in software engineering, you might have heard terms like unit tests, functional tests, integration testing. At Microsoft, we have our own terminology that we call L0, L1, L2, and L3. This really just means the number means how many dependencies are we testing. So L0 means we're not testing any dependencies, we're testing just a piece of code, a function. L1 means we have one dependency, which is usually the data layer, like a database. And when we get to L3, that's where you're actually testing the entire system, and that means you need a production instance to test against. And when I joined Microsoft, so this says current and future, but it's actually when I joined Microsoft back in 2017, and this is where we are today. A couple of years ago, we had primarily L3 tests, so these very expensive tests that have to be run against production, and we had very few L0 tests. We've completely transitioned that to where we have tons of L0 tests, these low-level unit testing, and very few tests that run against production. To see why that's actually beneficial, we can look at what kind of testing we can do and what time it takes to run those tests. So this is actual data from our engineering system. In our L0 test run, it takes 5 minutes, a little bit over 5 minutes, to run 63,000 unit tests. Whereas the equivalent L2 test, it takes 36 minutes to run only 2,000 tests. So you can see that if we can shift towards having more L0 tests, we have a much faster feedback loop. So if we make any code changes that break something, we get a much quicker feedback of what went wrong. The other huge advantage of moving towards these faster testing is that if it takes us 36 minutes to run tests, that means if there's any bug that I need to fix in production, it will take me at a minimum 36 minutes to get that change tested and out into production. In fact, it usually takes a few hours to get a fix out into production. So the more we can rely on these fast L0 testing, we can have a much faster turnaround when delivering new features and fixing bugs. So another key thing that we use in practice, and this is actually, it's a very simple concept, but it's actually very powerful in practice, is called feature flags. And what a feature flag is, it's basically an if-else condition in code, except that where you might have a if-else condition in code that's kind of statically just working only within the code, the flag is basically stored externally to the code. And what that means is that we're able to flip this feature flag on and off whenever we want, and it lets us control which part of the code we're running. Are we running the new piece of code or the old piece of code? And so whenever I want to make a code change, if I can put it behind a feature flag, I'm able to control who's using that new feature so that, for example, if we deploy to production and there's a bug in that code, well, if that bug we detected, we just flip that feature off and that bug goes away for customers. So that lets us go from, a 36-minute turnaround time to fix a bug to seconds to flip a feature flag on or off. And so there's a huge benefit when using these in practice. The other big thing, useful advantage of feature flags is that we can do A/B or split testing. So let's say, as an example, I'm making a change to speed up loading time for a web page. So I put my faster code behind the feature flag and leave the slower code in the else condition. So, and then what I can do is I can say enable this feature on some fraction of customers and let the other customers use the old version, and then look at the result. If I see the customers with my feature flag, my new faster page loading time, if it's actually faster, then we can keep that feature. If we see it's not really having any impact, then we need to go back and figure out what went wrong. And so by being able to do this kind of A/B testing, we're able to see the impact of changes we're making as we're making them. And in fact, you might have actually seen feature flags in practice. If you go to GitHub and look under your profile, you will see this feature preview link, and a lot of sites do this. that let you go and enable these features whenever you want to. So we have feature flags, we have our testing in place, but ultimately bugs still kind of get past that. Again, a lot of what we're doing is kind of putting in tools that we can reduce risk, but there's still always going to be a risk. So the next technique we can use is called safe deployment practices. And this is where we're actually deploying a change into production so it can be used by customers. So how can we deploy safely? Well, the first thing we want to do is we need to make sure our code works well. And so we actually deploy it to environments that we are using ourselves. And it's a term we call dog fooding. In the example of GitHub, all of our GitHub development is done on GitHub using a early release version of the software. So if we see any issues in that early release version, we can fix it before it gets out to the broader user base. And so if you imagine this conceptually, we essentially divide our users into this ring model, where we have these inner canary regions, which is basically us, the developers. You might have some early adopters, which are customers who signed up to get access to new features quicker, but they might also see more bugs because they're just in a higher risk ring. They get features quicker, but it might be more buggy. And hopefully we detect and fix all those bugs before it gets out to the broader user audience. So what's actually interesting about this is this entire process I show here of deploying out to production, going through these rings, this used to be a manual process. So at Microsoft, we actually had someone dedicated that we called a deployment driver, whose job was to actually just sit there and monitor the deployments and get them out into production. If there's a human in the loop, there's chances things go wrong because humans, as good as we can be, we're faulty. And so we want to transition this as much as we can to automation. And that's in fact what we've done since joining GitHub, that this entire process of deploying is now completely automated. When we deploy to one of these rings, we have automated checks to verify the health of the service. And if we detect that anything goes wrong, we can automatically roll back the change. And so in that way, one is we've eliminated the need to have someone dedicated to deploying our software. But two, it's all automated. If things go wrong, it just gets rolled back almost instantaneously. And so the impact to customers is greatly reduced. But what this also lets us do is ship faster. So back when I worked at Microsoft, we had 3-week milestones. And what that meant is every 3 weeks, we would take all of the changes that all of the engineers made in that 3-week period, and then we will release that into production. So if you remember, I said that we had about 6,000 changes a week. So in a 3-week period, we had 18,000 some code changes. And all of those would just get bundled up and deployed. And of course, as you might expect, things go wrong. So how do we improve upon that? Well, we deploy faster, and that might be a little bit counterintuitive. How does deploying faster actually reduce the number of issues you might see? Well, one reason is that each day when we deploy, we're deploying fewer changes. And so if something does go wrong, an engineer can quickly see what the problem was because we don't have 18,000 some changes to go and sort through to figure out what the problem is. We might only have 100 to go through. But also by deploying data or by deploying daily, we get very quick feedback from customers of the changes. And so we're able to quickly implement those changes into the code. Now, where we want to be in the future is to deploy every single change. So that means every single commit, we will test it, build it, deploy it, get it out to customers, and get feedback on it. We're not quite there yet. There's a lot of technical challenges to get there. But today we deploy daily, and it's been a huge advantage. It's a completely automated system, which is fantastic to see. So this is my last slide, but basically everything that I've talked about up until this point falls under what we would call DevOps. And DevOps is actually a much broader topic. It's way too much to go in one presentation, but the key idea here is that we're combining software development with IT operations. And the goal of all of this is we want to be able to have a faster time to markets. We want to be able to ship changes faster. We want to reduce the occurrence of errors. We want to shorten the lead time between fixes. So going back to that time it takes us to run tests, if it takes us 30 minutes to run all of our tests, that limits how quickly we can fix bugs for customers. And we also want to have faster mean time to recovery. So part of that means that as a software engineer, I have to be responsible for the day-to-day operations of these services. And so we're monitoring the live site health. We have on-call rotations. So when something goes wrong, it doesn't matter if it's in the middle of the workday or 3 a.m. in the middle of the night, I could get called for a problem and have to go and address it. So that's one of the things I tend to like less about this position, but it's also kind of a necessary evil of being a software engineer in today's environment. But yeah, so in review, we're deploying these services to the cloud. We kind of build in reliability, scalability, but ultimately it's kind of down to software engineers and code changes, being able to deploy quicker so that we can reduce the amount of changes that get to customers, and that in effect makes our software more reliable. So all of these things I've been talking about are really about reducing risk as we're deploying code. So that's all I had in my presentation, sorry. So I'm happy to take questions now. Feel free to ask me anything about my experiences at Microsoft and GitHub in addition to what I've talked about. I'm happy to share anything.
So I'll give time for folks to sort of formulate some questions, but we had an interesting conversation this morning, and I had asked you sort of what was the thing that was maybe surprising or that academia didn't prepare you for, and the way that you think about this. And you said it was problem framing and sort of the collaborative workflow. I don't know if you want to sort of talk through that a little bit in terms of what sort of the shocks and challenges and the things that problem framing and all of that that you're encountering that wasn't really in your training or your background before.
Yeah, so coming from an academic background, it's working in industry is completely different from what the kind of experience you might have in academics. The scale that we operate is completely different. You encounter problems when you're operating at the scale where you have millions of customers than what you might see if you're taking a class on software development. And they don't really teach you in classes how to address problems like that. So when I made that transition, it was a very big learning experience for me to pick up on how do we internalize these safe deployment practices? How do we write code that's safe to deploy? Kind of getting back to what you're talking about, part of this engineering process that we have is, I'm a software engineer. I get direction from my management, kind of the big vision of the future direction of GitHub, but it's really on the engineers to go and figure out the actual steps that we're going to take to reach that point. So it's actually really interesting to see that as an engineer, we're given that level of responsibility, but we're also expected to be able to go and manage these code projects to deliver new features and deliver it safely. So that's a huge difference between what you might see in academics versus industry.
So sort of that operationalizing environment where, because I assume upper level strategy can change on a week to week level, and you have that continual sets of feedback where they're visioning and then your teams are trying to make that a reality without breaking the system. I think it's pretty interesting. Any questions from audience?
Can I follow up to that, Pat? 'Cause David, I don't really see the transition in like what your research was in and how that transitions to what you're doing now at GitHub. Like that seems like very different. Like like your research and what you're doing now.
Yeah, so they are completely different. I made the transition due to life choices because my fiance was basically finishing her PhD and starting a postdoc, and so that's what led to this change. But it was a very dramatic change. I basically left academics behind. I left all of the work I've been doing on the optimization side of things and pretty much started as a software engineer. And yeah, so it's a very dramatic shift. I do try to dabble in some of the research sides. Like I continue to collaborate with Pat on some research, but my life today is completely different than what it was 5 years ago. But it's also, I think, personally, it's been I've enjoyed the experience. One of the things I found like most dramatic when I made that transition is the level of expertise that the people I work with is just astonishing. Like I work with some of the best engineers. Like Pat at the beginning, he will talk up everything that I've done and say how great I am, and I appreciate that. But I look at the people I work with and I think they're just amazing. Like they're the most talented people. And so it's humbling to work with them. It's educational. It's just been an amazing experience for me.
That's great to hear. I know most of us are PhDs here, or I think so. Do you regret doing your PhD then?
Sorry, say that again.
Do you regret doing your PhD?
Do I regret getting it?
Yeah.
I wouldn't. No. I definitely wouldn't have changed anything that happened. Again, it was the decision to transition was partly out of my control. I was never a fan of the teaching side of things. I was really into research and less about teaching. And so I don't think even with the PhD that I would have stayed much in academics. I would have been more on the research side. And that's kind of how things are today. Like, even though we're building a product and it's not research, we're inventing something new. We essentially have to make groundbreaking, like even though software development, we're researching as we go along. We don't publish like you might see in academics, but we definitely are kind of inventing new things.
Cool, thanks.
Other questions?
TC here. Great talk. I do have some questions regarding to virtual machines and cloud applications, if you don't mind. So we know that the cloud, for cloud, there's a big trend from the monolithic services to the microservices. And certainly with that change, there are a great stringent demand in the service level objectives, which from a few hundred milliseconds to just a single-digit milliseconds. How does the hardware does Microsoft team has did anything with regard to this change in SLOs?
Yeah, so I can talk more about GitHub since that's where I am now, but speed is critical to what we do. Like, people notice the difference between like a 100 millisecond page load and a 150 second page load. It's actually, we care about each millisecond that it takes. And what we try to do is, one is you can make code changes to make it faster. Like, do you need to cache data? Like, what data do you need to cache in memory and store in memory? But that also means that as you have millions of customers, what data is important for you to cache, because you can't cache like 1 megabyte of cache data per customer. When you're talking about millions of customers, that's a lot of data. And so we have to be very careful about, what data we're able to process, what data we need to access quickly. One of the advantages of using cloud services to help with SLOs is that we can move the data closer to the customer. And so if you're a European customer, we don't want you going across the Atlantic to access a data center in the US. We want that data as close to them as we can. And the Microsoft Cloud and Azure and the Amazon cloud kind of let you do that. We actually have technologies like there's point of presence nodes and edge nodes, where basically we can position these special nodes as close as we can to customers, like within cities. And once they access that node, they get onto the high-speed network that's provided by Azure or Amazon. And then that gets quickly to the server, so we can respond very quickly. So there's a lot of technical hardware that goes into also making it very fast for customers.
That's great. Do you mind also another question?
Yeah, go ahead.
So you talk about reconfiguring a virtual machine, about the vertically scaling up and horizontally scaling up. Why is it often a choice of horizontal? Is it because to repack a virtual machine is always about it's always introduce a lot of overheads, perhaps?
So yeah, so to scale up a virtual machine basically means that's not an online operation. So you have to stop the virtual machine, then create a new one using like the same data disk, but that has the more CPU, more RAM. So that's actually causes an outage of the service if we would have to scale up that way. By being able to just add or remove a brand new VM and just have a load balancer that distributes the traffic among them, that's a much easier way to go and increase the computing power we have. Since there's no outage, you have, say, 10 VMs currently running, and we just add another one to that. We're not actually like having to stop a VM and then recreate it.
So yeah, that's very good to hear. Thank you for your explanations. That's all for my question.
Sure thing. Thanks for the question.
Bertha, you had a question?
Yes, thank you. So I'm an animal scientist. I'm a faculty in the animal science department, so my question is not going to be nearly as sophisticated as others, but I am working on building a software program that would be used as a farm management tool. And we use GitHub for our development. But my question is fairly simple. I'm wondering if you have any general rules of thumbs in terms of the scale between the thing it's canaries, early adopters, and users in terms of the number of people in each of those groups?
Yeah, so like a canary, we're talking about like a couple hundred users. So a given scale unit in production can handle hundreds of thousands of accounts. So when I talk about account on like GitHub, we're talking about like a repository. So I think a couple 100,000 repositories per scale unit as the load. And that actually creates an important issue when I'm talking about like how we can safely deploy, because testing and validating code on like a canary region that's small has completely different issues than what you might see when you have a huge scale unit that has hundreds of thousands customers that's running very hot. Like the CPUs are very hot and we might need to scale up and down. The issues you face there are completely different. And so that does create some concern of this canary region doesn't really replicate what a production scale unit might experience. So there are some things we can try and do there. We can do some like load testing where we basically have some automated code that just goes and sends traffic to just exercise it more. Whether that simulates what you might see in practice depends. The other key distinction is we call this the data shape, but basically it's what we design. So when you talk about like the data a customer might have, like on GitHub, you have code, you have repositories, but some people might design their code so it's a mono repo, so you have a massive code base. Some people might design it as microservices, so you have really well-defined services spread across multiple repos. Those are different data shapes, and those have different implications on how do you make software fast, because you have more data, it takes more time to process that. And so we also have to be concerned about customers might be using our services like GitHub Actions in a way we didn't anticipate. And so it's difficult for us to test against that, but we also can see how they're using it and be able to react and essentially like make the system work for their use case.
Thank you.
Other questions for Dave?
Hi, Dave. I had one question. This is a little bit different, but I'm just curious. In any of the places you've worked in, Microsoft or GitHub, you always mention like the data centers and how the amount of energy that's being used is like on the order of like neighborhoods or like small towns. And I'm just wondering if, like, from an ethical perspective, if it ever comes through that, like, when you're developing, is there a conscious effort to sort of develop with respect to like how much energy is being used? Like, I'm sure that energy efficiency is really important for your cost anyway, but like lately, I think people have been talking about, especially in like AI, as like the amount of energy that's going to like train models and stuff is huge, and can we justify that cost? And I feel like our lives revolve around this, so we always find a way to justify that, like, this is just how it is. And I was just wondering if like that is an active part of the like discussion when these systems are being developed.
Yeah, so I wouldn't define it so much as in we're concerned about energy consumption, because I mean, part of that is like if you're running a VM that has some amount of energy it's consuming, it's more of a cost concern because, and cost is kind of going to map directly to energy usage in a case like this. At this point, we're more interested in growth than saying cost savings or energy savings at that point. But having said that, it's always a consideration because ultimately cost is going to be a key driver. Like, we're going to want to reduce it at some point and control that cost growth. So one of the advantages of going to the cloud is that we're able to use the economies of scale to make things like the energy consumption much more cost effective. If everybody's buying a personal computer to run code on, that personal computer needs like precious metals that have to get mined, that causes a lot of environmental damage, the power supply. And so going kind of to a cloud-based solution, you're able to somewhat minimize that because you're not relying on everybody to have a personal computer with all their hardware running. You can kind of offload that. The other thing is companies like Microsoft and Amazon, they're very conscious about energy supply, not only based on kind of the cost of it, but also the environmental impact. And I think Microsoft, I'd have to go and look up the articles, but I think they're striving for something like by 2050 to be like carbon neutral. And so we do look for ways of how can we use renewable sources of power, or how can we offload the carbon consumption, and invest in planting trees and other ways that you can capture the carbon that we are consuming by these data centers. And one actually interesting thing that goes along with that Pat and I talked about is like talking about like Bitcoin, because Bitcoin's like a new thing. Like, that uses the amount of power as like a small country. It's like insane, but, and like, yeah, there's definitely like, how do you deal with those moral questions of is it worth the potential environmental impact of something like Bitcoin mining?
Right, yeah. It's very interesting. Thank you.
Thank you.
So I have a sort of an ending question I think students might find interesting. So when you're in a place like GitHub and where you've been at in Microsoft, what is your utopian trajectory? Like, what is the ultimate cool professional sort of trajectory that you're sort of looking at, where your ambition is, what, in terms of the type of where you're going, what freedoms it affords you, that type of thing?
I mean, I'd say career-wise, it's like, of course, advancement within the company, but it's kind of getting to the point that as a software engineer, I can kind of be an individual contributor to projects. So that's something I really want to kind of focus on. In terms of technology, we've already talked a bit about microservices, but these are extremely complicated systems when you're talking about even just something like GitHub has hundreds of microservices that are operating. They all depend on one another in various ways. How do we quantify that? How do we analyze that? How do we guard against outages? If one service goes down, does that bring down GitHub, or does it just take down a small feature? And so that area is something I'm really interested in. There's a lot of research in chaos testing, where you basically can randomly inject faults into a complicated system like this and see how it reacts. So some places like Netflix do this a lot, and I think it's something that we as GitHub should do a lot more of. But we can actually take a production system and start injecting faults in it and see how it reacts. And it seems crazy that we actually do that with a production system, but that's the best way that we can learn from this, by using a actual system that has the same load that we might expect in production, see how it breaks and fix that. So I think there's a lot of potential that we can do there. It's something I'm personally interested in.
Could you say a little bit more of what an individual contributor means? Like, what does that actually mean?
So in kind of the Microsoft and GitHub lingo, it's kind of you as an individual. So Microsoft GitHub has different levels for software engineering. Like you get hired on as software engineer 1, 2, 3, senior, staff, and above. And the expectation at each level is that you kind of have more responsibility. And so the individual contributor is someone who's basically responsible for some section of the code. It could be a small piece, it could be a big chunk. So in like my case, I contribute heavily to GitHub Actions. And so as an individual contributor there, I would basically, as an individual, get direction from management and say like, hey, it'd be awesome if we could do this. And then it's my responsibility to go and design, implement, and deploy that new feature. So it's really just, it puts a lot of responsibility on you as a software developer, but I think it's also kind of exciting. It's cool to be able to have that level of control.
Excellent. Well, thank you for all your time today, and very much enjoyed your talk. And so I'll give you a digital clap and then let you escape to the million sort of probably burning fires that you have to go address, and hopefully you have some time to eat. So thank you, Dave, very much.
Thank you, everyone.